Okay, in this video segment, we're going to talk about our lead-in to the quantum mechanical model and also talk a little bit about something called electron duality. So, first of all, the last time we let off, we were talking about the planetary model and a little bit how the planetary model doesn't really do everything we need it to do in terms of describing the atom. Biggest issue was, if you look at Bohr's model, the premise that electrons orbit in a nice elliptical paths like planets is great, but if you actually do the math and the physics behind that, you find out that with the mass of the electron, the speed at which it's moving, and the nuclear attraction that's there, that the math doesn't work out, that the electron actually should not be able to hold in orbit like a planet could actually hold. So we knew that that model wasn't perfect, that wasn't really a great model because the physics didn't work out for the electron to orbit in that manner, okay? So we need another way of looking at the atom and saying, well, where do these electrons hang out, or how do they work if you're not going to have that kind of model? So here's a little video on this kind of lead into quantum theory.
In the early part of the 20th century, scientists found it difficult to understand the structure of atoms. Ernest Rutherford and his colleagues visualized them as negatively charged electrons circulating about a positively charged nucleus. A German physicist named Max Planck suggested that energy emitted or absorbed by an object could only be emitted or absorbed in discrete amounts or units. He called these units of energy quanta. Niels Bohr, a Danish physicist, visualized atoms much like our solar system, with the nucleus like a sun and the electrons orbiting it like planets. This is called the planetary model. He then applied Planck's idea of quanta to the behavior of the electrons surrounding the nucleus. He suggested that electrons' orbits depended on their amounts of energy. When an electron absorbs energy, it jumps from an orbit close to the nucleus to one further away. When an electron moves closer to the nucleus, it emits energy. In both cases, the energy is only in discrete quantities. Louis de Broglie, a French physicist, proposed that electrons were not only particles, but also a form of energy that acted in a wave-like manner. But the more evidence that was gathered, the more scientists came to understand that atoms were not like the solar system at all, because the electrons did not circle the nucleus in regular orbits. In one of the most significant developments, in 1927, Werner Heisenberg, a German physicist, showed that it was impossible to determine the precise location and velocity of an electron at the same time. All that could be done was to describe the probability of the location of electrons. This has come to be called the uncertainty principle. All of these ideas have come together into what is now called quantum theory, or quantum mechanics, one of the most important scientific advances of the 20th century.
Okay, so once we get through all these different scientist ideas, this idea of the quantum theory or the quantum model really can't be pinpointed down to any one scientist anymore. It's really a collaboration of work from a lot of different people from a lot of different areas. And if you notice, the people they talked about there, they were mathematicians and physicists. So we really are below the world of chemistry and the even more root stuff of physics and math right now. So first thing we want to talk about is this dual nature of electrons, which sometimes makes people's brains hurt a little bit. But what we figured out, and Louis de Broglie was the first person to kind of talk about this, is that electrons don't just act as particles, but electrons actually take on wave-like behaviors also, okay? Which can be kind of challenging to think of it that way, but we really just have to kind of accept the idea that electrons can both act as a wave and can act as a particle, okay? When electrons are moving as waves, they don't act like a mass anymore. So they don't have to move in linear pathways. They don't have to take time to get from one place to the other. They're now more like a light wave or something that has energy to it. Okay, so there's a video on that also that we will watch here to kind of give you an idea of how do we know the electrons actually act as waves and not as particles, and what experiment in particular kind of helped determine that electrons do act as waves. And this is called the double slit experiment. So here you go.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Okay. While that video may be a little bit challenging to understand and kind of conceptualize, what it does for us though is it kind of shows us that electrons must work as waves when they're around the atom, because if you have an electron moving as a wave, it's going to generate that interference pattern that we kind of see down here. When electrons act as particles, they are going to be like this. Okay. Now, one thing the video talked about is that observer, and the idea of the observer getting in the way and stopping the wave-like behavior comes from the fact that we can't observe anything without putting energy into it. Okay. So imagine like telescopes and microscopes and anything that kind of stuff that we use, they all need some sort of light source. So same idea with us. So we want to observe the electron, we need to somehow give it some energy so it can register with us, or it can give us a signature. Well, anytime we give it energy, it quits acting like a wave and starts acting like a particle. So it's really hard for us to kind of observe it directly without giving it energy. As a result, anytime we observe it directly, it acts as a particle. But if we indirectly observe the results of what it does, like in this interference pattern, we do see it acting like a wave. Okay? So take home is, we got to accept the fact that electrons act as waves, which means we need to have some conversation about waves. So a wave is a disturbance that transmits energy. So even water waves or sound waves, they're all different types of waves that push energy along. Okay? Now electrons, because they are able to do this, are considered a wave. They can act as a wave. They have a very specific wavelength, and that wavelength is based on whatever their mass is and the speed at which they travel. Okay? So because they have these very specific wavelengths, that limits where they can be located around the atom. All right? Now, Broglie was the first person to kind of talk about this as electrons moving as a wave. So if you think about it, if you have a certain radius that your energy level is away from the nucleus, you should be able to fit, if you have the right radius, the exact number of wavelengths around a nucleus. Okay? If you have the right radius, this wavelength pattern should be able to repeat on itself over and over and over again. And that's what an electron needs, is to be able to repeat itself over and over and over again. That's where it can be stable, that's where it can exist. If you take a look at this graphic, we see in this case we have n equaling 3, or 3 wavelengths, so this pattern can repeat itself 3 times. Over here we see the pattern repeating itself 4 times. However, any radius between 3 and 4, that pattern will not repeat. So since the pattern does not repeat, the electron can't exist there because the wave pattern cannot repeat on itself. In fact, what happens here, if an electron was to reside in this location, its wave-like behavior actually would cancel itself out and it would diminish or fall away. So electrons cannot be between levels 3 and level 4. That goes back to the planetary model saying that we have quantized energy. This idea of quantized energy matching up with the fact that electrons as waves can only have very specific positions around the nucleus. Okay? Now, that leads us into the quantum mechanical model itself and how that kind of works. So that will be our next video. Thank you.